It's a great pleasure for having Cynthia today, defending her PhD thesis, and thanks for joining us. Cynthia is my first PhD student, and as you know, you just start, you have your doubt, and who should I hire? Looking back, I feel very lucky I hired Cynthia in the lab. She built the lab with me, basically, the culture in the lab, helping other people. And I think usually people, in a PhD student, in the end, they feel they owe to their advisors because they help them write the papers and stuff like that. But I feel I owe Cynthia to help me build the lab. And I feel lucky to be on her papers, a lot of great papers in geometric deep learning. And these are really emerging topics in robotics. And we'll see in the future a lot. And without further ado, we're going to listen to Cynthia's talk.
Thank you, Mommy, for your kind introduction, and thank you everyone for being here. Today, I'm going to talk about multimodal geometric learning for robot localization. So to begin with, I'm going to start with a mini cheetah video that we took in the beginning of my PhD. That was during pandemic. We were walking mini cheetah around where we live on campus. Nowadays, robots can carry out a wide variety of tasks. And to do so, they need to have a role model of the environment, understand the environment, and estimate where their position and orientation is within this environment. And this estimation is called robot localization. And this is the task this thesis is interested in. To estimate robots' position, we often need some visual measurements. However, visual measurements can be completely different after transformations. So for example, these are two images that is the same tabletop with the same objects on top. Us as humans, we know they are the same just under different viewpoints. But for robot, they take these two measurements as completely different measurements and don't understand it is just under some transformation. So how can we let robot understand they're the same, just under some transformation? This is the question we want to answer in this thesis. We use geometric deep learning to help. Geometric learning is a method that embeds the geometric structure into the neural network and let robot understand those transformations. Before diving into detail, I want to introduce some key terms in geometric learning. One is called invariance. Invariance is the output is unaffected by the group action on the input. So for this example, the input image is being rotated, and the output feature we learn from the neural network stays unchanged. Another term is called equivariance. Equivariance is the group action on the input affects the output in the same way. So now the output feature we learn from the neural network is rotated along with the input image. In this thesis, we're interested in the group SC3. It is the group of 3D rigid transformation that includes 3D rotation and 3D translation, because most robot undergoes this transformation. In this thesis, we want to answer how can we leverage equivariance to enhance the robustness of robot localization under 3D rigid transformations. We propose SC3 invariant place recognition, that we learn SC3 invariant feature learning for a stable representation of a place to identify if we have been to the same place or not. We also propose SC3 equivariant transformer designs for learning point cloud correspondence matching and estimate the transformations between 2 point clouds. Next, we propose methodologies to fuse equivariant and non-equivariant models together. Lastly, all the code is open source and available online. I'm going to first talk about Chapter 3, the SC3 invariant point cloud-based place recognition. Place recognition is the task that robot determines if it has been to the same place or not. The robot can travel around in the world and then estimate a trajectory that has some accumulated error throughout the time. If we can identify these start point and the end point are the same place, they can eliminate this accumulated error. On the right-hand side, you can see this is often what the robot is facing. They have two measurements. They are comparing these two, say, point clouds, if they are representing the same place, and identify if this is the same place it has seen before. However, for the challenge for place recognition is that the feature we learn from neural networks are usually sensitive to the transformation changes in these 3D point cloud data. For example, if the vehicle changes lens, that will exist some translation changes. And if you are revisiting the same place in different orientation, there will be some rotation changes. And there could also just be random rotation and drift from the 3D point cloud data. So in this chapter, we want to learn the features that remain invariant. So we can identify the same place no matter how the measurements are being transformed. The existing methods are sensitive to 3D transformation. In the middle, we have a point cloud being rotated and translated. On the left-hand side is the representation that learned from the existing method. Their representation is sensitive to the transformation. So when the point cloud is being rotated, it keeps changing, and we cannot use this representation to identify if this is the same place or not. On the other hand, our method is able to provide a stable place representation. So even though the point cloud input is being rotated, translated, our representation stays the same, and we can use that for stable place recognition. In this chapter, we propose our framework for SE3 invariant place recognition. The input are 3D point clouds, and it can undergo optional attentive downsampling. Then we will learn local equivariant features, and then we will aggregate it together to be a global representation. First, I'll talk about how we can learn local equivariant features. We use some convolutional neural networks. Convolutional neural networks is in the product of function f and the translated kernel. The kernel translates through the pixels and learn the feature. Standard convolutional neural networks are translation equivariants. That means if the input is translated to the right, say the cat here in the image is shifted to the right, the feature we learn also shifted to the right. So standard convolutions are translation equivariant, but in the beginning I talked about we're interested in SE3 that includes rotation and translation. So how can we incorporate the rotation in this as well? We can use group convolution. Group convolution extends equivariance beyond translation to the group we're interested in. And here the equation shows the integral form, but in practice, we need to discretize. So for standard convolution, they discretize the translation onto the pixels. For regular group convolution, additionally, we also discretize the rotation and add additional group dimension in the feature to record the response over each discretization. So how can we discretize the rotation group? For 2D rotation, you can discretize the rotating angle. Say we discretize every 90 degrees. We can have designed the anchors to be on the vertices of this rectangle. That means we can use this anchor to use the configuration of these anchors to represent the current rotation. And for example, if this rectangle is rotating clockwise 90 degrees, now is the same rectangle, but we represent it using different configuration of the anchors. I'll do that animation again. So previously is this configuration, and then after rotation, it's another configuration of the anchors. For 3D rotation, we can use some finite rotation groups such as this octahedron to discretize the rotation. And we also define the anchors to be the vertices of the octahedron. Similarly, when we rotate the octahedron, it is just the changes of the configuration of the anchors. So for learning SE3 equivariant regular group convolution, we can learn features on each anchor. And then we can stack them together to be the feature we learn. We can use this to recover the rotation through the permutation of anchors. For example, the same example that we rotate the octahedron 90 degrees clockwise. Previously, the purple feature is on anchor 1. Now it moves to the anchor 4 position. When we stack the feature together, yes?
Yeah, how do you handle the non-commutativity? So you're playing it like a Rubik's Cube, right?
Mm-hmm.
The Rubik's Cube method.
Yes.
The permutation.
Yes. So this design, to explain this, you need exactly on your discretization for your rotation. In reality, it can have some interpolation between different angle degrees. Yeah.
Does that answer the non-commutativity, or maybe I didn't understand the answer?
Because we're not really multiplying, composing transformation. There is a transformation on learned features.
Okay, I mentioned that we can recover the rotation through permutation. And then we can also obtain invariant feature by doing max pooling. So for example, previously, the maximum value of these features is on the purple feature. After rotation, it is still on the purple feature. So when we do max pooling on these two features, we will get the same feature, same value from these max pooling. So we can obtain a stable feature even though the point cloud is under transformation. So previous page, I talked about how we learn local equivariant feature and invariant feature. Next, I'm going to talk about how we aggregate it together to be a global representation. Previously, the local features are a feature per point. For each point in the point cloud, we learn the feature. After that, we want to have a global representation for the whole point cloud. One method we can use is NetVLAT, that is to learn cluster centers to calculate distances between centers and local features. Another method is generalized mean, that is a pooling layer that generalizes the max pooling and me pooling. After we have the whole framework, we train on the Oxford robot car benchmark. Oxford benchmark is a data set that vehicles drives in a similar route at different times and seasons. They have total 45 sequences and 21,000 point clouds. We train on this data set, and then this is a quantitative result of the previous toy example that the point cloud is being rotated and translated. Existing method, when they compare the representation of the original point cloud with the representation of under different rotation degree and different translation, only with small rotation angle and small changes in translation, there will remain higher similarity. On the other hand, we can provide a stable representation no matter how the same point cloud is being rotated or translated. We also tested on some test sequences. These sequences are having place loop closure that is small range of rotation. Our method is comparable with state-of-the-art methods. These are tested on university sector, residential area, and business districts. We also want to make it more challenging. We tested on unseen data. So previously, the framework is trained on Oxford dataset, which is in UK. And then this is tested on Kitty dataset, which record in Germany, and with different sensor measurements as well. So the sensor measurements looks different, but our method is still able to generalize with this different input point cloud. We also want to make it more challenging. We are revisiting the place in opposite direction. So now there exists some rotation changes in the sensor measurements, the input point clouds. In this experiment, our method is able to maintain the performance because we already incorporate these transformation changes in our neural network. We also done some parameter analysis. We can achieve better performance with using lower number of parameters comparing to the baselines. So just a summary of this chapter. We propose a new SC3 invariant framework for place recognition using 3D point clouds. We also show that using geometric learning that improves robustness against the rigid transformation. However, during this study of this chapter, a question often comes up, that is, what happens if the scene is only partially observed? So that inspired our next chapter, that is SC3 equivariant transformer for low overlap point cloud registration. Point cloud registration is the task that finds the transformation between two point clouds and then align two point clouds together. However, there could be challenges such as what I mentioned before, there might just be low overlapping between these two point clouds. Another challenge is there might be large arbitrary transformation between these two point clouds, so make algorithms hard to have the initial guess of the transformation. Existing methods use the correspondence-based method to find the transformation. They first find the point correspondence, which point in point cloud A correspond to which point in point cloud B. Finding the correct correspondence is essential because the accuracy of point cloud registrations highly relies on the correspondence matching. Existing methods also show that transformers can help finding correspondence, because when we think of the transformer mechanism, which is also called attention, it is intuitively telling us where we should pay more attention to when comparing one input with another. So in the middle, this is an oversimplified example. That is one point cloud comparing to another point cloud. And for each point in point cloud A, compare with each point in point cloud B.
Turn it on, turn it off. That's what I thought.
Might just come back on its own.
Yeah.
Can you hear us?
Okay. I can do this. Yeah. So for here, we can use an overly simplified example that we compare each point in point cloud A with each point in point cloud B, and then learn where we should pay more attention to. Given the darker grid here is higher attention weight, that will give us the intuitive of which point correspond to which point, and then we can align them together. So this is the framework we propose for equivariant point cloud registration. We first learn equivariant features following the previous chapter, but we designed the encoder-decoder structure that we downsample and upsample the point cloud and learn the feature in each stage. Next, we propose the equivariant transformer to learn the point correspondence between two point clouds. After learning the point correspondence, we know which point match with another one. We can use this point matching information and use Rensack algorithm to estimate the transformation between two point clouds. So you can see the equivariant transformer part here is very complicated. I'm going to deep dive into each module we design. We designed 3 small modules, and then for each input of these modules are the equivariant features we learned from previous stage. So when I introduced equivariant feature learning in the previous chapter, we learned additional group dimension that encodes the response over the discretized anchor, discretized group for each anchor. So we want to design the transformer module that accommodate this group dimension, keep this group dimension while learning attention weights between points. We also designed another module that is learning the attention weights between different anchors. The next module we designed is learning the attention weight between discretized rotation. Previously, we mentioned that we can use the anchors in the group dimension to recover the discretized rotation using permutation. So we can also learn the attention weights between discretized rotation. And combine these different modules together, we can have this complete diagram. We have different modules that can use for learning point correspondence. We trained this framework on 3D match data set that is indoor environment for RGBD point clouds. We train on 20,000 point cloud pairs and then use the ground truth transformation to find the ground truth point matching for supervision. This is an experiment on rotated 3D low match that is only contain 10 to 30% overlapping ratio, which is low overlapping with random rotation. In this experiment, our method is able to perform better than baseline that is not equivariant. We also want to test how generalizable our method can be. So this whole framework was trained on 3D match dataset, which is indoor scenes, and then we tested on the outdoor scenes, the KITI dataset. This experiment also showed that our method is able to generalize to unseen data and then perform better multiple metrics. So summarize of this chapter, we proposed equivariant transformer designs for point cloud correspondence matching. We also shows that using geometric learning can improve the registration robustness on low overlap data. When doing this chapter of study, and a question often comes up is what about images and how can we fuse the geometric learning with foundation models? So that inspired our next chapter. That is multi-modal fusion for place recognition, integrating visual foundation models with 3D equivariant features. Foundation models are large models trained on large amount of data. It can be a foundation of a lot of downstream tasks and can generalize with unseen data. It has been done on languages such as ChatGPT, on visions, and also people are doing for robotics as well. However, foundation model lacked the understanding of geometric of the world. So we're thinking, what if we can combine it with the geometric learning that embed this geometric structure into the neural network, combine geometric learning with foundation model that can take the advantage of both sides. So we propose fusing geometric learning with foundation model. That is a multi-model approach. We have geometric features from point clouds, and then we have image features from visual foundation models. We also want to minimize changes in the foundation model architecture because it's expensive to retrain. For this chapter, we want to evaluate on the place recognition task that given the image and the point cloud, the robot determine if it is the same place or not. We propose 3 methods to fuse the equivariant and non-equivariant models together. Late fusion is using the global feature, and then invariant fusion and equivariant fusions are using local features. I'll first introduce okay, I'll try. This one?
Yep, last year.
Our first, does it work?
Hit the switch.
Yes. Can people hear me? No? Oh, it works now, okay. Okay, first introduce late fusion. Late fusion, we are using the global feature from the geometric learning model and the visual foundation model. It is already a global representation of the input point cloud. And then we fuse them together using direct sum. We tested, yes?
Direct sum or concatenation? I know in the thesis is direct sum, but the way you illustrate seems like concatenation.
Yes, so I think by definition, direct sum and concatenation are the same thing. Yes, it's concatenation and direct sum, to clarify.
Cleaning the literature.
What? I thought direct sum is adding together.
No, we track them as separate vector spaces. It's like mathematical directly.
Yes, it's concatenation.
Concatenation?
Yes.
Yeah. Okay.
CS department is VS Stack in Python.
Yes, so to clarify, this late fusion method is using concatenation or stack the feature together, or I call it direct sum here as well. We tested on the Oxford dataset. Here, the image and point cloud shows the same place, but we revisit this place at different time. So you can see one is at nighttime, one is at daytime. For the image, the illumination changed a lot, but for point cloud, it remained consistent. In this experiment on Oxford, the multi-modal approach can achieve better performance comparing to either one of the single model approach using just point cloud or using just image. We also tested on the Kitty dataset, which is the same day sequence, but we revisit the place at a different orientation. Using the multi-modal approach also outperform any single modality using just point cloud or using just the image. We also proposed invariant fusion. That is, we get the feature at the local level. So the feature we got from geometric learning is the local invariant feature. We fuse it with the the local feature of the image as well. So it's the feature per image patch. We fuse them together given the point and image patch correspondence using tensor product. The next method we propose is equivariant feature. Here we get the local equivariant feature from geometric learning. So now we have the group dimension that encodes the different response over different rotations. And here's the oversimplified example that discretizes over 90 degrees. We also get the local feature from the visual foundation model and fuse them together with tensor product. We experimented on the edge point lock dataset. That is a synthetic indoor RGBD data. So RGBD point cloud enable us easier to find the correspondence between the points and the image patches. So in this way, we can perform invariant fusion and equivariant fusion. For this specific example, invariant fusion performs better, but they all perform better than just doing late fusion. So for a summary of this chapter, we propose methodologies to fuse equivariant features with vision foundation model features. We also show that combining them together, we are able to provide stable representations when two modalities have different performance. In conclusion, we propose SE3 invariant feature learning for a stable representation of a place. We also propose SE3 equivariant transformer designs for point cloud correspondence matching to estimate the transformation between two point clouds. We also propose methodologies to fuse equivariant and non-equivariant models. Future work will include some equivariant breaking situations. Those are interesting to look into. One example is occlusion. Under different occlusion situation, the equivariance might break, and how can we address this kind of situation? Another things to look into will be how do we learn equivariance features for movable parts and deformable objects. Another interesting to look into is how do we represent the scene if it is dynamic. Another future direction to look into is multi-modal fusion for modalities other than image and point cloud. For example, we can add language. Language gives us a higher level of understanding. Or it can be visual language model that gives us a hierarchical scene understanding of how the scene is like. So here I present a list of publications and list of open source repositories. Now's the time for acknowledgement. I want to thank my committee and thank Moni for all the encouragement you gave me when the project stopped, when I got rejections, and then gave me the opportunities to grow as a researcher. I want to thank Jesse for your support throughout my time in Michigan, including the time I was just in master program as well. And also thanks Stella for giving me the computer vision perspective. And then I think you're the only professor I got to say hi during computer vision conferences. And also thank you, Katie, who's online today, for giving me valuable feedback and advices throughout my time in master as well and during the PhD thesis preparation. Also want to thank my collaborators. I want to thank Ray for being my early mentor during my PhD time, and Ming Han being my late mentor during my PhD time. Ming Han gave a lot of insights into the geometric learning, equivariant learning. And also other collaborators, Jingwei, Evelyn, Wendy, Avery as well, and then Sam. I don't have Avery's photo. And also thank you for Curly Lab, for your insightful discussions, and then always say yes to my crazy lab social ideas. I also want to thank Trivi and Justin for being the first batch with us, going through all the things at the same timeline. Next, I want to thank Michigan Robotics and NAME for giving me a supportive and collaborative environment. It's like a family here. There are too many people I cannot list it all, so just some pictures for people I interact the most, and especially thanks to Denise. I also want to thank Wire, thank Liz and Alia, grabbed me along to create Wire, and we have so many good memories in there. I also want to thank the Taiwanese group with mechanical engineering and robotics. We have a group of alumni and current students that can discuss things and give opportunities to each other. Also, big thanks to the friends that is always there, and thank you for being part of my life. And also thank you for my family, extended family, Justin, and my cat Hinoki. Thank you for unlimited love and support. That concludes my talk today for my thesis defense. Thank you.